In this video, we will cover session 11.3, Euler's method. Euler's method is a numerical method for finding approximate solutions to a differential equation. The idea is to approximate a solution curve by short line segments. So at a point xy, the slope of the solution curve is given by fxy. Thus, if data x is small, so we have a point xy. If this data x is small, we set data y is fxy times data x. So data y is this part. Then the point x plus data x, y plus data y is close to the solution curve. So here is a rough picture. So as you would expect, the smaller data x, the better the approximation. Numerical studies show that if data x is small, then making data x 10 times smaller makes the error about 10 times smaller. So now we look at an example. Use Euler's method for dy dx is y, this differential equation. Start at the points p0 is 0.1 and take data x is 0.1. So the slope at the point p0 is 1 is 1. 1. dy dx is equal to y coordinate is 1. So its slope at this point is 1. So as we move from p0 to p1, y increases by data y. This data y is slope at p0 times data x. So it's 1 times 0.1 is 0.1. So that in picture, it looks like this. So suppose here is the point p0. It's 0.1. So the slope at this point is 1. So this is slope is 1. And data x is 0.1. As data y we get is also 0.1. So this is 0.1. So we get here p1. P1 is here. This point is P1. So its y value is 1 plus 0.1. So it's 1.1. So the point P1, its coordinate is 0.1, 1.1. So this is when we move from P0 to P1. So now using the differential equation again, we see that the slope at P1, P1's y coordinate is 1.1, so its slope is 1.1. This slope is 1, so at P1 its slope is 1.1. So here its slope is 1.1. So if we move from P1 to P2, then y changes by data y, the slope at P1 times data x. So it's 1.1 times 0.1, so 0.11. So this is still data x. Then data y is 0.11. So this means y value at P2 is y value at P1 then plus delta y. So it's 1.1 plus 0.11. So this is its y coordinate of P2 is 1.21. Here is P2. It's P2. So we can continue do this. So continue continue this, we get a P3. Continue gives the results in this table: P0, P1, P2, P3, P4, P5. And this is the Euler's approximation solution here. This is the same as we sketched here. So since the solution curve of this differential equation are exponentials e to x, so they are concave up and bend upward away from the line segments of the slope field. Therefore, in this case, Euler's method produces y values which are too small. The solution curve is the exponential. So the Euler's method provides smaller y values. And you see the coordinates. You see the points P1, P2, P0 are below this exponential curve.